Alright, so the chapter of this title is typed out as reaction rates. You'll often see it titled kinetics. So if we think back to the thermodynamics chapter where we talked about delta H and delta S and delta G and all that stuff, think about delta G. What do we care about for delta G? Not its value, but whether it was positive or negative. So Gibbs free energy, I care if it's positive or negative. If Gibbs free energy for a reaction is negative, we know the reaction is, that's delta H. Spontaneous. Okay, so a negative delta G means a spontaneous reaction. So that's when we talked about if a reaction will happen or not. But if you tell me you're going to do something, that doesn't tell me anything about how quickly you're going to do it. All right, that just means you're going to do it in the future. So for this chapter, we'll look at primarily how quickly reactions happen, or the rates of reactions. So most of the reactions we've looked at so far, pretty much all of them, the rate didn't matter because they pretty much happen instantly. If you think back to the double replacement lab where you filtered out and weighed your solid product, when you dumped the two solutions together, there was no wait period between them mixing and a solid forming, right? But the reactions we do are chosen for that reason. There is no wait time. But for most chemical reactions, there is some sort of rate going on. They're not instantaneous. We have to calculate and look at how long it's going to take. So I've got a little video from just an example of a reaction. So that's just an example of a reaction that's not quite instantaneous. What happened there was you have two reactions going on. The first one's pretty slow, and the second one's very fast. So it looked like a delay than an instant reaction, right? What's really happening is we're having a slow reaction to begin with and a fast reaction. Most of the reactions we'll look at have the same rate over time, so they slowly occur. So instead of all of it being made at once, or a long delay, then it's all made, an amount is gradually made over a long period of time. So the definition we'll have for kinetics, we'll just say it's the study of reaction rates. And then it gives you below a little definition of rates. It just says it's the change over time of bonds breaking and or bonds forming. So if I think about a very simple reaction, just something like A turns into B, does the rate at which A disappears equal the rate at which B appears? Yes. So could I measure either one of those to find the reaction rate? Yes. And we'll talk about it later. It depends on how easy one is to measure. Okay. In the video we watched, it's easier to measure the appearance of products because they're a distinct color. But in some situations, the disappearance of reactants might be easier for us to recognize. So we'll look at both bonds breaking and bonds forming there. So you can read those sentences for yourself later. Kind of gives you an idea of why we care about reaction rates and time. But for now, let's go ahead and talk about what we call collision theory. So the definition of collision theory is typed up for you. It says it's a series of ideas which help explain or predict the kinetics, so the rates of a reaction, any factor which increases or decreases the number of effective collisions, which is underlined, between the reacting particles will speed up or slow down the reaction. So in order for two particles to react, they have to do what? You got to physically touch each. They got to get close together, right? They have to collide. So notice that doesn't say collisions; it says effective collisions. Okay. So think about if we're trying to high five. Instead of high fiving, I smack you on the back of the head. Did we collide? Yes. But in terms of high fiving, is that an effective collision? No. So the same thing for reactions. We can have collisions that aren't necessarily effective. Okay, so we define an effective collision as a collision, so a hitting of particles between two reactants, which results in a reaction. So there are two criteria that we have to meet for a collision to be effective. The first one is proper orientation. So let's back to the high-fiving deal. If my hand hits your head, is that proper orientation for the high five? No. Okay. And the other one can be, if I come into the high five very, very slow with very little energy, we're just holding hands and not high-fiving. Okay? So you have to have sufficient energy. So two particles can collide, and if there's not enough energy for them to react, they'll just bounce away and go on with themselves. Okay? They won't react. So the proper orientation doesn't always apply. Let's think about an example where it does and doesn't apply. So first, if we have, I'll write it up here, Ag, Aq plus Cl minus Aq yields AgCl solid. What is the general shape of that silver and chloride? What's the general shape of most atoms? Kind of spherical-ish, right? We can say they're generally spherical, okay, just for the sake of this. So if I have a silver ion, chloride ion, we know they're not really spherical, but for the sake of this, we can assume they are. Is there any way those two spheres can collide with each other that's not the proper orientation? No. Is one side of that silver different than the other side? No. So does the whole proper orientation play a role here? No. That's a pretty simple reaction though, right? Just two atoms. But if you think back to last year, talking about enzymes and proteins and things of that nature, what do you know about the size of most proteins relative to a single atom? Proteins are a lot bigger, and they can be hundreds or thousands of atoms. So if you think about a protein, just with hundreds and hundreds of atoms, and all different atoms, okay, together in a specific way, the protein's all folded up. If this protein reacts with chloride, it might only react with chloride in one very specific location. Does that ring a bell a little about proteins? So if it only reacts in this one specific location over on this side, is it now possible for chloride to collide with that protein in a way that a reaction does not occur? Yeah. Because there's a big portion of that protein that's not going to react, okay? So now, with larger molecules, proper orientation gets more important, okay? With our very simple examples, it's not so important, okay? But the energy issue always is. Does that make sense? Good. So now, let's look at the next statement. It says, the greater the number of effective collisions, the blank, we'll fill in rate, of a chemical reaction. So fill that in. The greater the number of effective collisions, the blank the rate of reaction. Greater or lesser? Greater. So what do you have to have a reaction? An effective collision. So the more effective collisions you have, the greater the rate of the reaction, the faster it goes. It's kind of logical, right? Okay. So before we get too far into that, a couple of vocab words we'll describe here. First is activation energy. We typically abbreviate it capital E, lowercase a, so it's often read as energy of activation. That way the E and the A are in the right order. You may have an idea what an activation energy is.
How much energy you need to have a reaction?
Yeah, so one way to think about it is how much energy you need to have the reaction. Okay, probably a better definition for us is the energy required to form an activated complex. We'll describe what an activated complex is in a minute, but for now, we'll just say it's the energy required to form an activated complex. Does anybody have by right now? You probably call it a transition state if you are, it's an activated complex. But an activated complex and transition state are very, very similar things. So we'll come back to what activated complex is in a minute. But think back for just a second about the whole delta H situation from a couple of weeks ago. What does delta H stand for? Change in enthalpy. So if the delta H for a reaction is -3, for example, what is the delta H for the reverse reaction? Which is positive 3, right? So for delta H, the forward and reverse just have negative signs. Here it's a little bit different, okay? But we still have to consider the activation energy of the reverse reaction. So we denote that with a little apostrophe, we call it a prime. So now we have EA apostrophe or EA prime. So EA prime is just the activation energy of the reverse reaction. So you could also say it's the energy required to form an activated complex of the reverse reaction. So now, what is an activated complex? So 2 notes on it. Before we say what it is, first let's say it is very unstable. It is a high energy particle. So typically, unstable and high energy go together. So we can now define it as the temporary situation when old bonds are breaking and new bonds are forming. So it's the very brief moment in time for a reaction when the old bonds are being broken and the new bonds are being formed. It is temporary, it doesn't last very long, we can't isolate it because it's very unstable. So if it's very unstable, is it going to stay like that for very long? No, it's going to go away. Okay. So let's think about a very simple example. Let's think about if I have 3 carbons bonded together. And we'll say that's a part of a much larger molecule. We'll focus on these 3 carbons. And there's a chlorine on the center carbon. And I want to add an iodine to it, an iodide, I-1. I'll go ahead and tell you the product for this hypothetical situation. It might be this. Okay. And we left off the rest of the molecule, all the hydrogens and oxygens and whatnot. So we go from this to this, plus Cl-1. That probably looks somewhat familiar, right? You just replace one atom with the other. We've done stuff similar to that. But at some point in the middle here, there's going to be a situation where the bond to chlorine is breaking and the bond to iodine is forming. Okay. That is called what? An activated complex. Is it stable? No. Does it last very long? No. We typically put it in brackets just to show it doesn't last very long. It's temporary. It's a transition state. So, which has more energy? The activated complex or just the reactants? The activated complex. So what do we call the energy I have to add to the reactants to get to the activated complex? The activation energy. Okay. Make sense? So now let's turn over to the next page and look at some hopefully familiar diagrams. Do these look familiar? That's not good. Yes. So if you think back, they were annotated last time. The energy diagrams for endothermic and exothermic reactions. So if I have to label these platforms as products and reactants, which is products? The right one. Reactants is up here. And hopefully you can tell me, without it being labeled, that this is exothermic, right? The products are lower in energy than are the reactants, so energy was lost. So exothermic, endothermic is the opposite. So the quickest way, or the best way, to get from reactants to products will just be a straight line down through there, right? But based on this, is that the route or the pathway the reaction takes? No. For some reason, it goes way up in energy here. Then it kind of tops out. What do we call this right here where it tops out? What's this called? Yes, the activated complex. Is the activated complex high in energy? Yes. Is that the highest energy point on this diagram? Yeah. So now, what do I call the energy required to get me from the reactants all the way up to the activated complex? The activation energy. So EA. So we can't just go straight from reactants to products because the middle point there, the activated complex, is high in energy. So we have to go to that high energy state and then become products. What would I call this? The energy difference between here and there. So what's the symbol for that? Delta H react, yeah. Good job. So the delta H here is negative because it's exothermic. So if there were numbers on this, could you, or on the y-axis, could you tell me the actual activation energy? Yeah. Could you tell me the energy of the activated complex, and the reactants, and the products, all that good stuff? Yeah, just reading the graph. Go ahead and label this one. Label the endothermic chart. Reactants, products, activated complex, activation energy, and delta H of reaction. Then look up and check it with mine. The sign for the delta H of reaction for the endothermic reaction is going to be what? Positive. So we talk about, or questions about that first? Okay. We talk about all this, or all that, to say this. There are 5 major factors that influence, the notes label it the number of effective collisions. The number of effective collisions directly determines the reaction's what? Rate. Okay. So there are 5 major factors that determine the rate of a reaction. We're going to go through those and look at those. Some of them we can use to control the reaction's rate. Others we can do nothing about, but they still affect the rate of the reaction. So the first one that we have listed, number 1, is the nature of the reactants. So what that means, for example, is it aqueous ions, covalent gases, etc. Okay. So primarily we're thinking about is it ionic or covalent? So can we really do a lot about changing this situation? If it's ionic, it kind of is what it is, right? Covalent is what it is. It does affect the rate, but we can't manipulate this. So before we talk about it, let's think back to the last chapter. Ionic compounds in water do what? When they dissolve. They dissociate. Covalent compounds in water, unless they're acids, do what when dissolved in water? Nothing. Okay. So glucose in water just dissolves, doesn't do anything. Okay. So that's kind of the difference that leads us to this. So first let's fill in the rule, and we'll talk about it. Okay. Solutions of ionic compounds generally react more quickly upon combination than solutions of covalent compounds. And it tells you that covalent or molecular interchangeable compounds can be organic or inorganic. We're going to save the organic chapter for May and put it to it last. So what does an organic compound mean? It has carbon. So it's not important here. We'll just come back to it later. That's our rule. Typically, ionic solutions react faster than covalent solutions. So let's write out two examples of reactions. You can think about why. So I'll write up here. I'll write H2 gas plus O2 gas yields H2O gas. Then I can say Ag plus Cl minus yields AgCl. And don't worry about balancing the first one. You can if you want to. It doesn't feel like. So the first reaction produces what type of compound? Ionic or covalent? Covalent. Water's covalent. Are the reactants covalent or are they ions? Covalent. H2 and O2. The second one. Does it produce an ionic or a covalent compound? Ionic. Okay. AgCl is an ionic compound. Are the reactants ions or are they just covalent molecules? They're ions. Okay. Let's think about the first example. H2 plus O2 yields H2O. So H2 and O2 are just flying around the room. And to react, they have to collide with proper orientation and sufficient energy, right? So first of all, what are the odds that two given particles even collide? Very high or very low? Pretty low, right? Is there anything attracting that hydrogen to that oxygen from across the room? No. They're just bouncing around. But eventually, just at a random chance, would they collide? Yeah. Would we expect this to be fast or slow if there weren't many particles? Probably pretty slow, right? They're just flying around randomly. But then think about the second situation. Ag plus 1 is floating around in solution. Cl minus 1 is floating around in solution. They have to collide with proper orientation and energy to react. But do they have to wait for random chance to collide? No. What are they doing to each other? They're attracting. Why? Yeah, the positive and negative attract each other. Okay? So that silver and that chloride are attracted to each other. They're being pulled together by an electrostatic force. They're not waiting for a random chance. So if this reaction waits for a random chance, this reaction, the two reactants are attracting each other, which do you expect to be more, or have a greater rate, happen faster? The second one. Because the reactants are attracted to each other. The first one, they're just kind of randomly bouncing around. Okay? Does that make sense? So when you see the situation, ionic typically occurs faster than covalent. That's the reason why. Be able to explain that. Okay? You could be asked in terms of number of effective collisions or in terms of reaction rate. Okay? Questions about that? So the notes give you two examples you can kind of look at on your own at some point. First example is double replacement lead 2 nitrate potassium iodide, making lead 2 iodide. The lead 2 and the iodide are attracted to each other. So if they're attracted to each other, that's pretty quick. Okay? Did anybody, when we did the double replacement lab, make the bright yellow solid product? No, that's what this is. This was an option. So when you dump the two solutions together, you immediately see a bright yellow solid product. But then on the back, there's an example of a reaction that is covalent compounds, covalent molecules. It is much slower. It requires us to do extra things to it to make it react because the nitrogen and hydrogen aren't necessarily attracted to each other the way the lead and the iodine are. Okay? So any questions about the first factor that affects rate of reaction? Okay? So the second one is a little more logical. It's concentration. So somebody give me a rough definition for concentration. Wish a test on it.
Molarity.
That's a unit of concentration.
How much of a solid and liquid?
How much something is in a certain space, right? So we can say amount of matter per unit area. So molarity is our common unit. So moles is my amount of matter. My unit area is liter. Okay. So we can use this to measure number of solute particles in a solution, or even number of gas particles in a container. Okay. So just using logic here, if you increase concentration, are you going to increase or decrease the number of effective collisions? Probably increase, right? If there's 2 y'all in this room versus 50 y'all in this room, which one's more likely to collide with somebody? You have 50 people, right? So if you increase concentration, you're going to increase the number of effective collisions. So there's 2 ways in a solution to increase the concentration. One is to add more what? What's the name of the thing we dissolve? Solute. Okay, so add more solute. The other is to take away solvent. That's a little more difficult. Typically with solutions you add more solute. But if you have gas particles, can you pretty easily decrease the space the gas is in? That's a little more easy. So in that picture on there, which is more concentrated? The left or the right picture? The right. I just decreased volume, which increased pressure. So which is more likely to have a greater rate? The right one or the left one? The right one, because it's far more concentrated, right? So the general rule is, the greater the concentration, the what? Higher or lower the rate? The greater the rate. That one should be pretty logical to us. Questions about the first 2 factors that affect rate? Okay, we'll stop there for today. Do the last 3 tomorrow. We'll go over the test real quick.